So last time we were looking at base units and derived units. We said we could combine units mathematically. Now we want to take a look at how we actually do that and some examples of what we get when we combine units mathematically. So here we have a couple example problems, and we want to just go through and see what's going on with these units. Okay, so I have this unit at the beginning, kilogram meter per second, times a per second, or 1/seconds. What is the combination? How do we combine units? Well, this is multiplication, so it's okay that we have multiple units in here. So I think we're going to go ahead and we're just going to say, well, let's take a look at what we have and then just do the math, right? It's just algebra.
Right. It's just like kilograms, you could think of as X, and meters, you could think of as Y, and S, you could think of as Z.
Okay.
It's just units instead of the letters you're used to. So if we got kilograms times meters per second here, then we kilogram times meter, I'm just rewriting this a little bit, per second, times 1/S.
And so now we're just multiplying fractions. So we're going to end up with a kilogram times a meter. And then a second times a second is a second squared.
Just like doing
Algebra. Okay. So when we combine the kilogram meter per second and a per second, we end up with a kilogram meter per second squared. Okay? And so that's what happens when units combine. What if we have the next example where we have seconds on top and seconds on bottom?
So we have kilogram meter per second squared here times seconds. Now you could think of this as seconds over 1, or we could just leave it as seconds. Now, kind of like in algebra, cross out the top and one of those on the bottom, so that square just becomes a 1. So we have kilogram meter per second now.
Okay. So multiplication and division, everything looks good there. Now, one of the things that's handy about this is sometimes we'll be using math, we'll be checking some formulas out, and we want to know, are we doing things right? And a good way to check to see that we might be doing things right is to see if our equation is valid. That is to say, if we're trying to find a distance, then the units on both sides need to be measured in meters. If we're trying to find a mass, the units on both sides need to be measured in kilograms. But if the units on one side don't match the units on the other side, we know we did something wrong. Okay? So if the units do match, we don't know for sure that the equation is right. But if they don't match, we know for sure the equation doesn't work.
Right, we don't want to use an equation where the units on both sides don't agree with one another.
You can't say kilograms equal meters.
Yeah.
Meters measure length. It's a different dimension altogether than mass. Okay?
Right.
So this problem right here, we have, this actually finds the radius of an inscribed circle in a triangle. Okay? And it says check the validity of the equation. Basically, do the units on the left side match the units on the right side? Well, first we have to tell you what each one of these things measures. S in this equation is actually the semi-perimeter of a triangle, so it's a length. It's how far around a triangle there we go. A is one side of the triangle, it's a length measured in meters. B is a length measured in meters. C is a length measured in meters. Those are the lengths of the triangles. And then R, of course, the radius of a circle measured in meters as well. So what we're going to do with this is just check to see that our units actually match up. So if we take a look, I have S minus A.
Okay, S is in meters, A is in meters. I can take meters and subtract meters.
So this arithmetic here is valid because I do have meters minus meters. And when I take meters minus meters, I'm going to end up with a distance measured in meters.
Now that wouldn't have worked if S was in kilograms and A was in meters, because we couldn't have taken kilograms minus meters.
Doesn't make sense. Okay. Again, meters minus meters, so I have meters again and meters again, and then S is also meters.
And we want to see if that's equal to
Well, the
units
radius
on the left.
is a distance, so that should also be measured in meters. So does this giant thing simplify down to meters?
Question mark there, because we're checking.
Check. Well, meters, this meter can cancel that meter. So that leaves me with the square root of meters squared. And so yeah, I do actually have meters. So I have meters on the right, meters on the left. And so this is a valid equation in terms of its units. Dimensionally, it makes sense.
Great. If we got meters on the left and meters squared on the right, we would have said this equation doesn't make sense and we don't want to use it ever.
It's focused. Meter squared is actually, it makes sense to talk about square meters.
Right.
It's an area, it's a surface. It doesn't make sense to call a surface a length.
Right.
Right. And then one more thing we can do is we can say, well, here is a valid equation. What do the units of this constant have to be in order for it to be a valid equation? And we're going to actually have to do this later. We're going to be examining relationships between variables. And a lot of times there's this weird constant we have to deal with, and it has a unit. Okay? So this equation says velocity is equal to the square root of twice g times m divided by delta x. Okay? So we've got a lot of stuff going on, and we're supposed to figure out what the units of g are.
Okay, so we don't know what G's units are. But it's gotta be some combination of meters and seconds and kilograms, it's like.
So let's go ahead and just replace the values here with their units. V says it's meters per second.
So meters per second on the left is equal to,
Square root 2. 2 is just a constant number. It has no units at all. So I'm not going to even bother rewriting.
all we're looking at now is the units. We don't care about any constants in here.
G, I don't know. I'm leaving it there. M, it says over here is kilograms.
So let's put in kilograms for
We're
that.
putting kilograms for that. Delta X, it says, is meters. Okay. Now, you got a square root on one side, and I don't like radicals, so the easiest thing to do is square
Right, let's
both
square
sides.
everything.
Okay. Now, remember, when you square a fraction, you square the numerator and the denominator. So I have meters squared per second squared equals g times kg over m. And now, I think we just want to go ahead and multiply both sides by m. So that cancels that.
Remember, our goal is to solve for G, so it's kind of like solving for X in math, so
Right.
it's G now.
So meters cubed over seconds squared equals
Equals G.
g times kg. So I'm going to multiply both sides by 1 over kg. That's the same as dividing by
Divide by
kg, right? So this kg cancels that kg, but if I did it to one side, I have to do it to the other. Okay? So 1 times m is just m, and so I'm left with meters cubed per kilogram second squared equals g. Okay, well, and I shouldn't really say equals, because
Those are the units of G.
these are the units.
So it could be like, G is equal to 25 meters cubed per kilogram second squared.
Right.
We're gonna
But
put a number on it
we're going to put a
later.
number in there later, but for now, the units of g are meters cubed per kilogram second squared. Okay? So this is called dimensional analysis. You just treat each unit as an algebraic quantity, and then you are able to figure out if your equation is valid, what the unit should be, and check your work.